Hello, this video is for section 8.3. We're going to be discussing determinants and Cramer's rule. And the determinant of a matrix is just a number. Usually it ends up being an integer, and it describes different properties of a matrix. First, let's compute the determinant of a 2 by 2 matrix. If we look at the equation over here, the determinant of A, which can also be represented by the absolute value symbols. We also represent it with vertical bars indicating that we're taking the determinant of the entries inside, and it's equal to A times D, which is the first diagonal, minus B times C, the second diagonal. So if we look at example A, we'll take the first determinant, which is the first diagonal, 2 times 4, minus the second diagonal, 3 times -1. This gives me 8 plus 3, which equals 11. So the value of the determinant of A is 11. Here we'll take the determinant of A, which is equal to the product of the first diagonal minus the product of the second diagonal. We get -12 plus 12, and that equals 0. One of the things about a determinant is that it tells us if there is an inverse for the matrix, and we'll be getting to that in section 8.4. As a brief preview, if the determinant is 0, there is no inverse. Again, we'll get to that in section 8.4. Now we'll find the determinant of a general matrix. Now this process is a little bit complicated, so bear with me. First, we need to indicate a row of the matrix. It doesn't matter which row you pick, but we need to indicate which row we are going to use. Second, we need to know the signs that are hidden in that row. And the way we find those signs is we create a checkerboard pattern of pluses and minuses, where the first entry is a plus, and then it alternates, just like a checkerboard. And these will be the signs of our rows. Now that we have indicated which row we're going to use, we're going to write out smaller matrices. So I'll take the first coefficient 1, and I'm going to multiply it by some matrix. This matrix is what's left over when I remove the column associated with the coefficient, in this case 1. So the remaining matrix is 0, 0, 3, 6, 2, 6, 4, 0, 9. I'll now move to the next number in our original row. And this time I'm going to use a minus as indicated in our plus minus pattern above. Now I'll write the next matrix, but this time we're eliminating the second column, and the remaining matrix is 0, 0, 3, 5, 2, 6, 2, 0, 9. The next sign that I'll use is a plus according to our pattern, and this will be 0 times a remaining matrix. So this time we'll move the eliminated column to the third column, and I'll write the remaining entries as my matrix. 0, 0, 3, 5, 6, 6, 2, 4, 9. My next symbol is a minus. The coefficient is a 4. And this time we're removing the fourth column. And I'm left with 0, 0, 0, 5, 6, 2, 2, 4, 0. Now we're going to repeat the process for each of these four terms. So let's look at the first term. We're going to have a leading coefficient of 1 in front of the entirety of this reduced matrix. So we'll take another row. In this case, I'll take 0, 0, 3. The first entry is going to be a positive, 0. The remaining matrix will be 2, 6, 0, 9, because we remove that first column. We're left with 2, 6, 0, 9. Now we'll alternate our signs, minus 0. The remaining matrix is 6, 6, 4, 9. Now we'll have a positive 3, and that will be times the remaining matrix, 6, 2, 4, 0. I'm going to repeat this now for each of the remaining matrices. I'll mark off a row, mark off a column, and reduce it down. 0 times 2, 6, 0, 9 minus 0 times 5, 6, 2, 9 plus 3 times 5, 2 2, 0. Now for this third term, since I have a plus 0, it doesn't matter what it reduces down to. It'll still always be 0 because the leading coefficient is 0. So I can skip that one. Then I have minus 4 times. Now here's something else. If I use this top row of all zeros, then each of our leading coefficients are 0, and that entire inside bracket will be 0. Sometimes it's good to write these out vertically and then compute them as individual pieces. These last two are going to be 0, so they're not going to matter much in the end, but these first two will have some values. Now again, since some of these leading coefficients are zeros, we won't have to compute them. So I'm going ahead and marking these out. And I've reduced this down now to 1 times 3 times the determinant of 6240, which is the main diagonal minus the second diagonal. This gives me 1 times 3 times negative 8, which is negative 24. And for the second big term, we've got negative 2 times 3 times the main diagonal, 5 times 0, minus 2 times 2. Gives me negative 2 times 3 times negative 4, which gives me 24. Adding in the negative 24, the 24, the 0, and the 0, the determinant of A then, negative 24 plus 24 plus 0 plus 0 equals finally 0. This matrix does not have an inverse. And that's what we can tell from the fact that the determinant is equal to 0. I understand that's a long process, so do look over this. We are going to learn a shortcut soon for determinants of 3 by 3 matrices, but it only works for determinants of 3 by 3 matrices. You must use this process for anything greater than 3 by 3s. So let's do the shortcut. We call this the crosshatch method. So the crosshatch method. So we'll start off writing out the determinant of b, placing the entries 2, 1, 0, -1, -2, 4, 3, 1, and -3. And what we'll do is append on the first two columns, 2, -1, 3, 1, -2, and 1. And this is where it's similar to the 2 by 2. We're going to take the three main columns and multiply them together. So we'll take 2 times -2 times -3 plus 1 times 4 times 3 plus 0 times -1 times 1. Now we're going to take the other diagonals and instead of adding them, we're going to subtract them. So we'll take now these three main diagonals and subtract them. So minus 3 times -2 times 0, minus 1 times 4 times 2, minus -3 times -1 times 1. And now I'll compute each of these products and combine them all. So 2 times -2 times 3, that's 12, plus 1 times 4 times 3, 12, plus 0. Now we're doing the second row, minus 0, minus 8, and negative times -3 times -1 times 1 is -3. And now I'll combine all these. 12 plus 12, 24, minus 11 is 13. That is a shortcut only for 3 by 3 matrices. Do not use that for 4 by 4 matrices, only for 3 by 3. Now we're going to use Cramer's rule to solve a system of 2 variables and then next a system of 3 variables. Now Cramer's rule uses determinants to find the values of x and y. But first we're going to need to find the determinant of the constants. So we'll set out the constants of our x's and our y's, in this case a 2 by 2, and we'll compute them. So 2 times 2 minus 1 times -1, and that gives me 5. Now we'll determine the determinant with x replaced by what the equations are equal to. So what that means is we're going to, instead of write the coefficients for x, we're going to write -9 and 8. We're replacing the x column with what the equations are equal to. The y's will stay by themselves. And this gives me -9 times 2 minus 8 times -1. That gives me -18 plus 8, which is -10. X then is equal to the determinant with the x divided by the determinant of the constants. So -10 divided by 5 gives me -2. We'll find d sub y, the determinant, with the y coefficients replaced by what the equation is equal to. We'll compute that determinant. 2 times 8 minus 1 times -9 gives me 16 plus 9, which is 25. That means y is equal to d sub y over d sub c, which is 25 divided by 5, which gives me 5. The solution then to this system is -2, 5. Now we're going to use Cramer's rule for a system of 3 by 3. So the first, I need to compute d sub c. So I'm going to find the determinant of the constant matrix, making sure I place zeros for any missing entries. And here I can use the crosshatch method to quickly compute the determinant. And so I'll multiply the three main diagonals, 1 times 0 times 0, and add them together, plus -1 times 1 times -1, plus 2 times 3 times 2. And I'll subtract out the second diagonal, -1 times 0 times 2, minus 2 times 1 times 1, minus 0 times 3 times -1. And if I combine these, make the math a little easier, cross out any of the 0 entries. So that's 1 plus 12 minus 2, which gives me 11. Now we're going to solve for x by replacing the x column with what the equations were equal to. 0, 11, and 0, and leave the remaining ones the same. And we can use the crosshatch method again by writing the first two columns to the end and multiplying the main diagonals. Now I'm going to speed this process up a bit by, instead of writing out the products, I'm just going to write what they're equal to. So the first main diagonal is 0 plus -1 times 1 times 0 is 0, plus 2 times 11 times 2 is 44, minus 0 minus 0 minus 0. So I get 44. That means x is d sub x over d sub c, which is 44 over 11, which gives me 4 for x. Now I'll solve for y by replacing the y column now with 0, 11, 0, and keeping all the rest of the coefficients we had. I'll append on the first two rows, 1, 3, -1, 0, 11, and 0, and multiply the main diagonals, 0 plus 0 plus 0, and subtract out the second diagonals. This time we're subtracting out -22 minus 0 minus 0. Combining all that, we get 22. So y is equal to d sub y over d sub c. 22 over 11, y equals 2. Now we'll solve for z. So we'll replace the z column, leaving the rest the same. So z column becomes 0, 11, and 0. I'll append on the first two columns to use the crosshatch method that only works for 3 by 3. So we get 0 plus 11 plus 0 minus 0 minus 22 minus 0. So when I combine all that, I get -11. So z equals d sub z over d sub c. Gives me -11 over 11. So z equals -1. Therefore, the solution to this system is 4, 2, -1. And that's it for this video.